covers examining and configuring the RBAC interface for controlling access, granting access to a central set of users by connecting with an LDAP service, configuring a FIRNet key to encrypt secrets in the database, securing traffic between your browser and the web server, fetching secrets from a central secret management system. Given the nature of Airflow, a spider in the web orchestrating a series of tasks, it must connect with many systems and is therefore a desirable target to gain access to. To avoid unwanted access, in this chapter we discuss the security of Airflow. We cover various security-related use cases and elaborate on these with practical examples. Security is often seen as a topic of black magic, where the understanding of a plethora of technologies, abbreviations, and intricate details is deemed necessary. While this is not untrue, we wrote this chapter for readers with little security knowledge in mind, and hence highlight various key points to avoid unwanted actions on your Airflow installation, which should serve as a starting point. Airflow interfaces. Airflow 1.x comes with two interfaces. The original interface, developed on top of Flask Admin. The RBAC interface, developed on top of Flask App Builder, FAB. Airflow initially shipped with the original interface and first introduced the role-based access control, RBAC interface, in Airflow 1.10.0. The RBAC interface provides a mechanism that restricts access by defining roles with corresponding permissions and assigning users to these roles. The original interface is, by default, open to the world. The RBAC interface comes with more security features. While writing this book, the original interface became deprecated and was removed in Airflow 2.0. The RBAC interface is now the one and only interface, so this chapter covers only the RBAC interface. To enable the RBAC interface running Airflow 1.x, set Airflow_webserver_RBAC equals true. Section 13.1. Securing the Airflow web interface. Start the Airflow web server by running Airflow web server and go to this link, where you will see a login screen, figure 13.1. This is the first view of the RBAC interface. At this point, the web server is asking for a username and password, but there are no users yet. Section 13.1.1. Adding users to the RBAC interface. We'll create an account for a user named Bob Smith. This creates a user with a role named admin. The RBAC model consists of users which are assigned to a single role with permissions, certain operations, assigned to those roles, which apply to certain components of the web server interface, figure 13.2. In listing 13.1, the user Bob Smith was assigned the role admin. Certain operations, for example edit, on certain components, such as menus and specific pages, for example connections, can then be assigned to a role. For example, having the can edit on connection model view permission allows us to edit connections. There are 5 default roles. The admin role grants all permissions, including access to the security view. However, think wisely about which role to grant a user in a production system. At this point, we can sign in with username Bob Smith and password top secret. The main screen will look just like the original interface, but the top bar has a few new items, shown in figure 13.3. The security view is the most interesting feature of the RBAC interface. Opening the menu displays several options, figure 13.4. Click List Roles to inspect all default roles, figure 13.5. In the List Roles view, we see the 5 roles available to use by default. The default permissions for these roles are given in Table 13.1. The just created Bob Smith user was assigned the admin role, granting him all permissions. Several permissions were omitted from Figure 13.5 for readability. You might note the public role has no permissions. As the role name implies, all permissions attached to it are public. That is, you do not have to be logged in. Say you want to allow people without an Airflow account to view the Docs menu, figure 13.6. To enable access to these components, we must edit the public role and add the correct permissions to it, figure 13.7. The permissions are quite fine-grained. Access to every menu and menu item is controlled by a permission. For example, to make the Docs menu visible, we must add the Menu Access on Docs permission. And to make the Documentation menu item within the Docs menu visible, we must add the Menu Access on Documentation permission. Finding the correct permissions can be cumbersome at times. It is easiest to inspect the other roles to learn which permissions are available. Permissions are reflected by a string, which in most cases should be self-explanatory about the access it provides. Section 13.1.2, Configuring the RBAC interface. As noted, the RBAC interface is developed on top of the Flask App Builder (FAB) framework. When you first run the RBAC web server, you will find a file named webserver_config.py in $airflow_home. FAB can be configured with a file named config.py, but for clarity, this same file was named webserver_config.py in Airflow. So, this file contains configuration to FAB, the underlying framework of Airflow's RBAC interface. You can provide your own configuration to the RBAC interface by placing a webserver_config.py file in $airflow_home. If Airflow cannot find the file, it will generate a default one for you. For all details and available options in this file, refer to the FAB documentation. It holds all configurations for the RBAC interface, not just those that are security related. For example, to configure a theme for your Airflow RBAC interface, set app_theme equals sandstone.css in webserver_config.py. View the FAB documentation for all available themes. Figure 13.8. Section 13.2, Encrypting Data at Rest. The RBAC interface requires users to exist in the database with a username and password. This prevents random strangers just looking around from having access to Airflow, but is far from perfect. Before diving into encryption, let's look back at Airflow's basic architecture from Figure 12.1. Airflow consists of several components. Every piece of software is a potential threat, since it serves as a path through which uninvited guests can gain access to your systems. Figure 13.9. Lowering the number of exposed entrance points, that is, narrowing the attack surface, is therefore always a good idea. If you must expose a service for practical reasons, such as the Airflow web server, always ensure it's not accessible publicly. Footnote 1. In any cloud, it's easy to expose a service to the internet. Simple measures you can take to avoid this include not using an external IP address and/or blocking all traffic and allow listing your IP range only. Section 13.2.1. Creating a Fernet key. You also want your data to be secure after an intruder has managed to gain access. Before creating any users and passwords, ensure encryption is enabled on your Airflow. Without encryption, passwords and other secrets, such as connections, are stored unencrypted in the database. Anybody with access to the database can then also read the passwords. When encrypted, they are stored as a sequence of seemingly random characters, which is essentially useless. Airflow can encrypt and decrypt secrets using a so-called Fernet key. Figure 13.10. The Fernet key is a secret string used for encryption and decryption. If this key is somehow lost, encrypted messages can no longer be decrypted. To provide Airflow with a Fernet key, we can generate one. Then we can provide it to Airflow by setting the Airflow_core_Fernet_key configuration item. Airflow will now use the given key to encrypt and decrypt secrets, such as connections, variables, and user passwords. Now we can create our first user and safely store their password. Keep this key safe and secret, since anybody with access to it will be able to decrypt secrets. Plus, you will not be able to decrypt secrets if you ever lose it. To avoid storing the Fernet key in plain text in an environment variable, you can configure Airflow to read the value from a bash command. For example, cat/path/to/secret instead. The command itself can be set in an environment variable. airflow_core_fernet_key_cmd equals cat/path/2/secret. The file holding the secret value can then be made read-only to only the Airflow user. Section 13.3. Connecting with an LDAP service. As demonstrated in Section 13.1, we can create and store users in Airflow itself. In most companies, however, there are typically existing systems in place for user management. Wouldn't it be much more convenient to connect Airflow to such a user management system instead of managing your own set of users with yet another password? A popular method for user management is via a service supporting the LDAP protocol, Lightweight Directory Access Protocol, such as Azure AD or OpenLDAP, which are called directory services. Note: throughout this section, we will use the term LDAP service to indicate a directory service supporting queries via the LDAP protocol. A directory service is a storage system, typically used for storing information about resources such as users and services. LDAP is the protocol via which most of these directory services can be queried. When Airflow is connected to an LDAP service, user information is fetched from the LDAP service in the background upon logging in. Figure 13.11. We first give a small introduction into LDAP and its corresponding technologies, section 13.3.1, and next demonstrate how to connect Airflow to an LDAP service, section 13.3.2. Section 13.3.1. Understanding LDAP. The relationship between SQL and a relational database, that is, PostgreSQL or MySQL, is similar to the relationship between LDAP and a directory service, for example, Azure AD or OpenLDAP. Just like a relational database stores data and SQL is used to query the data, a directory service also stores data, albeit in a different structure, and LDAP is used to query the directory service. However, relational databases and directory services are built for different purposes. Relational databases are designed for transactional use of any data you desire to store, while directory services are designed for high volumes of read operations, where the data follows a phone book-like structure, for example, employees in a company or devices within a building. For example, a relational database is more suitable for supporting a payment system, since payments are made often and payment analysis involves different types of aggregation. A directory service, on the other hand, is more suitable for storing user accounts, since these are requested often but usually do not change. In a directory service, entities, for example users, printers, or network shares, are stored in a hierarchical structure named a directory information tree, DIT. Each entity is called an entry, where information is stored as key value pairs named attributes and values. Also, each entry is uniquely identified by a distinguished name, DN. Visually, data in a directory service is represented like figure 13.12. You might wonder why we demonstrate this hierarchy and what the abbreviation DC, OU, and CN stand for. While a directory service is a database in which you can theoretically store any data, there are set LDAP requirements for how to store and structure data. One of the conventions is to start the tree with a so-called domain component, DC, which we see in figure 13.12, represented as DC equals COM and DC equals Apache Airflow. As the name suggests, these are components of the domain, so your company domain is split by the dots. For example, Apache Airflow and COM. Footnote 2. The standards are defined in RFC 4510 to 4519. Next, we have OU equals people and CN equals Bob. OU is short for organizational unit, and CN is short for common name. While nothing is telling you how to structure your DIT, these are commonly used components. The LDAP standard defines various object classes, which define a certain entity together with certain keys. For example, the object class person defines a human being with keys such as SN, surname required, and initials, optional. Because the LDAP standard defined such object classes, applications reading the LDAP service are certain to always find the surname of a person in the field named SN, and thus any application that can query an LDAP service knows where to find the desired information. Now that we know the main components of a directory service and how information is stored inside, what exactly is LDAP and how does it connect with a directory service? Just like SQL provides certain statements such as select, insert, update, and delete, the LDAP provides a set of operations on a directory service. Table 13.2. For only fetching user information, we will require the operations bind to authenticate as a user with permissions to read users in the directory service, search to search for a given DN, and unbind to close the connection. A search query contains a set of filters, typically a DN selecting part of the DIT, plus several conditions the entries must meet, such as UID equals bsmith. This is what any application querying an LDAP service does under the hood. Footnote 3. LDAP search requires installation of the LDAP-UTILS package. Applications communicating with an LDAP service will perform such searches to fetch and validate user information for authentication to the application. Section 13.3.2. Fetching users from an LDAP service. LDAP authentication is supported via FAB. Therefore, we must configure it in webserver_config.py in $airflow_home. When configured correctly and upon logging in, FAB will search the LDAP service for the given username and password. If found, FAB will allow the found user access to the role configured by auth_user_registration_role. At the time of writing, no feature exists to map LDAP groups to Airflow RBAC roles. Footnote 4. It is possible to manually edit the table AB_user_role in the Metastore to assign a different role after the first login. With LDAP set up, you no longer have to manually create and maintain users in Airflow. All users are stored in the LDAP service, which is the only system in which user information will be stored, and all applications, including Airflow, will be able to verify user credentials in the LDAP service without having to maintain their own. Section 13.4. Encrypting traffic to the web server. An intruder can obtain data at various places in your system. One of these places is during the transfer of data between two systems, also known as data in transit. A man-in-the-middle attack, MITM, is an attack where two systems or people communicate with each other while a third person intercepts the communication, reading the message, potentially containing passwords and such, and forwarding it so that nobody notices the interception. Figure 13.13. Having secrets intercepted by an unknown person is undesirable, so how do we secure Airflow such that data in transit is safe? The details about how a man-in-the-middle attack is performed are not in the scope of this book, but we will discuss how to mitigate the impact of a man-in-the-middle attack. Section 13.4.1. Understanding HTTPS. We can work with the Airflow web server via a browser, which communicates with Airflow through the HTTP protocol, figure 13.14. To communicate with the Airflow web server securely, we must do so over HTTPS, HTTP Secure. Before securing traffic to the web server, let's understand the difference between HTTP and HTTPS. If you already know this, you can skip to section 13.4.2. What is different with HTTPS? To understand how HTTPS works and what the private key and certificate are for, let's first establish how HTTP works. When browsing to an HTTP website, no checks are performed on either side, user's browser or web server, to verify the identity of the request. All modern browsers display a warning of the insecure connection, figure 13.15. Now that we know HTTP traffic is not secure, how does HTTPS traffic help us? First, from a user's perspective, modern browsers will display a lock or something green to indicate a valid certificate, figure 13.16. When your browser and a web server communicate over HTTPS, the initial handshake involves more steps to verify the validity of the remote side, figure 13.17. The encryption used in HTTPS is TLS, Transport Layer Security, which uses both asymmetric encryption and symmetric encryption. Whereas symmetric encryption applies a single key for both encryption and decryption, asymmetric encryption consists of two keys, public and private. The magic of asymmetric encryption is that data encrypted with the public key can only be decrypted with the private key, which only the web server knows, and data encrypted with the private key can only be decrypted with the public key, figure 13.18. At the start of an HTTPS session, the web server first returns the certificate, which is a file with a publicly shareable key. The browser returns a randomly generated session key to the web server, encrypted with the public key. Only the private key can decrypt this message, which only the web server should have access to. For this reason, it's important to never share the private key. Anybody with this key is able to decrypt the traffic. Section 13.4.2, Configuring a Certificate for HTTPS. Airflow consists of various components, and you want to avoid attacks on and between all of them, regardless if they're being used externally, for example, exposed on a URL such as the web server, or internally, for example, traffic between the scheduler and database. Detecting and avoiding a man-in-the-middle attack can be difficult. However, it is straightforward to render the data useless to an attacker by encrypting the traffic. By default, we communicate with Airflow over HTTP. When browsing to Airflow, we can tell if the traffic is encrypted by the URL, http or https://localhost:8080. All HTTP traffic is transferred in plain text. A man in the middle reading the traffic could intercept and read passwords as they're transmitted. HTTPS traffic means data is encrypted on one end and decrypted on the other. A man in the middle reading HTTPS traffic will be unable to interpret the data because it's encrypted. Let's view how to secure the one public endpoint in Airflow, the web server. You will need two items: a private key, keep this secret; a certificate, safe to share. We will elaborate on what these items entail later. For now, it's important to know the private key and certificate are both files provided by a certificate authority or a self-signed certificate, a certificate you generate yourself that is not signed by an official certificate authority. Both the private key and certificate must be stored on a path available to Airflow, and Airflow must be run with the following. See these paths. Start the web server and you will see that http://localhost:8080 does not serve the web server anymore. Instead, it is served on https://localhost:8080, figure 13.19. At this point, traffic between your browser and the Airflow web server is encrypted. While the traffic can be intercepted by an attacker, it will be useless to them since it's encrypted and thus unreadable. Only with the private key can the data be decrypted. That's why it's important to never share the private key and to keep it in a safe place. When using the self-signed certificate, as generated in listing 13.5, you will initially receive a warning, Chrome displayed in figure 13.20. Your computer holds a list of trusted certificates and their location, depending on your operating system. In most Linux systems, the trusted certificates are stored in /etc/ssl/certs. These certificates are provided with your operating system and agreed on by various authorities. These certificates enable you to go to https://www.google.com, receive Google's certificate, and verify it in your pre-trusted list of certificates, because Google's certificate is shipped with your operating system. Whenever your browser is directed to a website that returns a certificate not in this list, your browser will display a warning, as is the case when using our self-signed certificate. Therefore, we must tell our computer to trust our generated certificate, knowing we generated it ourselves and therefore trust it. Footnote 5. Various technical details are omitted for clarity. Storing billions of trusted certificates for all websites is impractical. Instead, few certificates high up in the chain are stored on your computer. Certificates are issued by certain trusted authorities. Reading a certificate should enable your browser to find the certificate's issuing authority and their respective issuing authority, and again, until one of the certificates in the chain is found on your computer. How to tell your computer to trust a certificate differs based on the operating system used. For Mac OS, it involves opening keychain access and importing your certificate in the system keychain, figure 13.21. After this, the certificate is known to the system but still not trusted. To trust it, we must explicitly trust SSL when encountering the self-signed certificate, figure 13.22. If you're hosting Airflow on an address accessible by others, that is, not localhost, everybody will have to go through the hassle of trusting the self-signed certificate. This is obviously undesirable. Therefore, you issue certificates by a trusted authority that can be validated. For further reading, search the internet for TLS certificate for purchasing a certificate, or Let's Encrypt for generating DNS-validated certificates, providing you with encryption. Section 13.5. Fetching credentials from secret management systems. Many companies apply a central secret storage system, enabling them to store secrets, passwords, certificates, keys, etc., just once in a single system, and applications are able to request the secrets when needed without having to store their own. Examples include HashiCorp Vault, Azure Key Vault, AWS SSM, and GCP Secrets Manager. This avoids scattering secrets over various systems and instead keeps secrets all in a single system that is designed specifically for storing and managing secrets. Additionally, these systems provide features such as secret rotation and versioning, which you do not get in Airflow. Secret values in Airflow can be stored in variables and connections. Wouldn't it be convenient and secure to connect with one of these secret storage systems instead of having to copy-paste secrets into Airflow? In Airflow 1.10.10, a new feature was introduced named Secrets Backend, which provides a mechanism to fetch secrets from external secret storage systems while still using the existing variable and connection classes. At the time of this writing, AWS SSM, GCP Secret Manager, and HashiCorp Vault are supported. The Secrets Backend provides a generic class that can be subclassed to implement and connect with your own desired secret storage system. Let's view an example using HashiCorp Vault. As you can see in listing 13.5, there is no explicit reference to HashiCorp Vault in your DAG code. The simple HTTP operator makes an HTTP request, in this case to the URL set in the connection. Before the existence of secrets backends, you'd save the URL in an Airflow connection. Now we can save it in, among others, HashiCorp Vault. There are a couple of things to point out when doing this. Secrets backends must be configured with Airflow_secrets_backend and Airflow_secrets_backend_quarks. All secrets must have a common prefix. All connections must be stored in a key named con_URI. All variables must be stored in a key named value. The secret name is stored as a path. This applies to all secret managers. For example, secret/connections/secure_API, where secret and connections can be seen as folders used for organization, and secure_API is the name identifying the actual secret. Note, the secret prefix is specific to the Vault backend. Refer to the Airflow documentation for all details of your secret backend of choice. The hierarchical organization of secrets in all secret management systems allows Airflow to provide a generic secrets backend to interface with such systems. In the Secrets Engines section in HashiCorp Vault, the secret would be stored as displayed in figure 13.23. Within a secret engine in Vault, we create a secret with the name connections/secure_API. While the prefix connections/ is not necessary, Airflow's secrets backend takes a prefix under which it can search for secrets, which is convenient for searching within just one part of the secret hierarchy in Vault. Storing an Airflow connection in any secret backend requires setting a key named con_URI, which is the key Airflow will request, figure 13.24. The connection must be given in URI format. The URI will internally be passed to Airflow's connection class, where the proper details are extracted from the URI. Say we have an API running on hostname secure_API port 5000, and it requires a header with the name token and the value supersecret for authentication. To be parsed into an Airflow connection, the API details must be stored in URI format, as displayed in figure 13.24. See this link. In Airflow, we must set two configuration options to fetch the credentials. First, Airflow_secrets_backend must be set to the class reading the secrets. HashiCorp Vault, airflow.providers.hashicorp.secrets.vault.vault backend. AWS SSM, airflow.providers.amazon.aws.secrets.systems_manager.systems manager parameter store backend. GCP Secret Manager, airflow.providers.google.cloud.secrets.secrets_manager.cloud secrets manager backend. Next, various details specific to the chosen secrets backend must be configured in Airflow_secrets_backend_quargs. Refer to the Airflow documentation for all details of all secret backends. Take, for example, backend_quargs for Vault. See the following. Here, the URL point to Vault's URL. Token refers to a token for authenticating against Vault, and connections_path refers to the prefix to query for all connections. In the Vault backend, the default prefix for all secrets, both connections and variables, is set to secret. As a result, the full search query given a con_ID, secure_API, becomes secret/connections/secure_API. The secrets backend does not replace secrets stored in environment variables or the Airflow metastore. It's an alternative location to store secrets. The order of fetching secrets becomes the following. 1. Secret backend. 2. Environment variables, Airflow_con_star and Airflow_variable_star. 3. Airflow metastore. With a secret backend setup, we outsource the storage and management of secret information into a system developed specifically for that purpose. Other systems can also connect to the secret management system so that you only store a secret value once, instead of distributing it over many systems, each with the potential for a breach. As a result, your attack surface becomes smaller. Technically, the number of possibilities to breach into your systems are limitless. However, we've demonstrated various ways to secure data both inside and outside Airflow, all with the goal of limiting the number of options for an attacker and safeguarding against some of the most common ways attackers gain unwanted access. On a final note, ensure you keep up to date with Airflow releases, as these sometimes contain security fixes, closing bugs in older versions. Summary. In general, security does not focus on one item, but involves securing various levels of your application to limit the potential attack surface. The RBAC interface features a role-based security mechanism to allow certain actions to the groups in which users are organized. Interception of traffic between the client and the Airflow web server can be made useless by applying TLS encryption. Credentials in Airflow's database can be made unreadable to an attacker by encrypting the secrets with a Fernet key. A secret management system such as HashiCorp Vault can be used to store and manage secrets so that secrets are managed in one single location and shared only when needed with applications such as Airflow. Chapter 14. Project: Finding the fastest way to get around NYC. This chapter covers setting up an airflow pipeline from scratch, structuring intermediate output data, developing idempotent tasks, implementing one operator to handle multiple similar transformations. Transportation in New York City, NYC, can be hectic. It's always rush hour, but luckily there are more alternative ways of transportation than ever. In May 2013, Citi Bike started operating in New York City with 6,000 bikes. Over the years, Citi Bike has grown and expanded and has become a popular method of transportation in the city. Another iconic method of transportation is the yellow cab taxi. Taxis were introduced in NYC in the late 1890s and have always been popular. However, in recent years, the number of taxi drivers has plummeted, and many drivers started driving for ride-sharing services such as Uber and Lyft. Regardless of what type of transportation you choose in NYC, typically the goal is to go from point A to point B as fast as possible. Luckily, the City of New York is very active in publishing data, including rides from Citi Bikes and yellow taxis. In this chapter, we try to answer this question. If I were to go from A to B in NYC right now, which method of transportation is fastest? We've created an Airflow mini project to extract and load data, transform it into a usable format, and ask the data which method of transportation is faster, depending on the neighborhoods you're traveling between and the time of the day. Footnote 1. Some of the ideas in this chapter are based on a blog post by Todd Schneider. See this link, where he analyzes the fastest transportation method by applying a Monte Carlo simulation. To make this mini project reproducible, a Docker Compose file was created running several services in Docker containers. This includes the following: 1 REST API serving Citi Bike data, 1 file share serving yellow cab taxi data, min.io, an object store that supports the S3 protocol, PostgreSQL database for querying and storing data, a Flask application displaying results. This gives us the building blocks shown in Figure 14.1. Our goal throughout this chapter is to use these building blocks to extract data from the REST API and share and develop a data pipeline connecting these dots. We choose min.io since AWS S3 is often used for data storage, and min.io supports the S3 protocol. The results of the analysis will be written to the PostgreSQL database, and the web page will display the results. To get started, ensure your current directory holds the dockercompose.yml file and create all containers. This exposes the following services on localhost: port with username/password given between parentheses. 5432 Airflow PostgreSQL Metastore, Airflow/Airflow. 5433 NYC Taxi Postgres DB, Taxi/RideTLC. 5434 Citi Bike Postgres DB, City/Cycling. 5435 NYC Transportation Results Postgres DB, NYC/TR4N5P0RT4TI0N. 8080 Airflow Web Server, Airflow/Airflow. 8081 NYC Taxi Static File Server. 8082 Citi Bike API, Citi Bike/Cycling. 8083 NYC Transportation Web Page. 9000 min.io. See the following. Data for both the Yellow Cab and Citi Bikes rides has been made available in monthly batches. NYC Yellow Taxi, see this link. NYC Citi Bike, see this link. The goal of this project is to demonstrate a real environment with several real challenges you might encounter and how to deal with them in Airflow. The datasets are released once a month. 1-month intervals are quite long, and therefore we've created 2 APIs in the Docker Compose setup that provide the same data but on intervals configurable to a single minute. Also, the APIs mimic several characteristics of production systems such as authentication. Let's look at a map of NYC to develop an idea for determining the fastest method of transportation, figure 14.2. We can clearly see that city bike stations are based only in the center of New York City. To give any meaningful advice about the fastest method of transportation, we are therefore limited to those zones where both city bikes and yellow cab are present. In section 14.1, we will inspect the data and develop a plan of approach. Section 14.1, Understanding the Data. The Docker Compose file provides two endpoints with the yellow cab and city bike data. Yellow cab data here, city bike data here. Let's examine how to query these endpoints and what data they return. Section 14.1.1, Yellow Cab File Share. The yellow cab data is available here. Data is served as static CSV files, where each CSV file contains taxi rides finished in the last 15 minutes. It will keep only 1 full hour of data. Data older than 1 hour is automatically removed. It does not require any authentication. The index returns a list of available files. Each is a CSV file holding the yellow cab rides finished in the last 15 minutes, at the time given in the file name. We can see each line represents one taxi ride, with a start and end time and start and end zone IDs. Section 14.1.2, City Bike REST API. The city bike data is available here, which serves data via a REST API. This API enforces basic authentication, meaning we have to supply a username and password. The API returns city bike rides finished within a configurable period of time. This query requests the city bike rides finished in the last hour. Each record in the response represents one ride with city bike and provides latitude-longitude coordinates of the start and end location, as well as the start and end time. The endpoint can be configured to return rides at smaller or larger intervals, where period can be minute, hour, or day. The amount is an integer representing the number of given periods. For example, querying this would return all city bike rides finished in the last 3 days. The API knows no limitations in terms of request size. In theory, we could request data for an infinite number of days. In practice, APIs often limit compute power and data transfer size. For example, an API could limit the number of results to 1,000. With such a limitation, you would have to know how many bike rides, approximately, are made within a certain time, and make requests often enough to fetch all data while staying under the maximum 1,000 results. Section 14.1.3, Deciding on a Plan of Approach. Now that we've seen the samples of the data in listings 14.3 and 14.4, let's lay out the facts and decide how to continue. To compare apples with apples, we must map locations in both datasets to something in common. The yellow cab ride data provides taxi zone IDs, and the city bike data provides latitude-longitude coordinates of the bike stations. Let's simplify, enabling our use case, but sacrificing a little on the accuracy by mapping the latitude-longitude of city bike stations to taxi zones, figure 14.3. Since the yellow cab data is only provided for 1 hour on the file share, we must download and save it in our own systems. This way, we build a collection of historical taxi data over time, and can always go back to the downloaded data if we change our processing. As mentioned, the Docker Compose file creates a min.io service, which is an object storage service, so we'll use that to store the extracted data. Section 14.2. Extracting the data. When extracting multiple data sources, it is important to note the time intervals of the data. The yellow cab data is available at 15-minute intervals, and the city bike data interval is configurable. To make it easy, let's also request city bike data at 15-minute intervals. This allows you to make 2 requests at the same interval, in the same DAG, and process all data in parallel. If we choose a different interval, we have to align the processing of both datasets differently. Section 14.2.1, Downloading City Bike Data. With Airflow, we have the simple HTTP operator to make HTTP calls. However, this quickly turns out to not suit our use case. The simple HTTP operator simply makes an HTTP request, but provides no functionality for storing the response anywhere. In such a situation, you are quickly forced to implement your own functionality and call it with a Python operator. Footnote 2. By setting xcom_push equals true, you can store the output in XCOM. Let's see how to query the Citybike API and store the output on the min.io object storage. We have no Airflow operator to use for this specific HTTP to S3 operation, but we can apply Airflow hooks and connections. First, we must connect to the Citybike API using the Python requests library and min.io storage using the S3 hook. Since both require credentials to authenticate, we will store these in Airflow to be loaded at runtime. By default, the S3 hook communicates with AWS S3 here. Since we're running min.io on a different address, we must provide this address in the connection